When I talk about black holes and space-time warping, I am really talking about gravity at its most extreme. And when gravity becomes extreme, it connects to almost every big question in cosmology: dark matter, dark energy, the expansion of the universe, and how the universe might end. So I want to walk through what we actually know, how we know it, and where the gaps in our understanding still sit. I will start with the basic idea. In everyday life, we think of gravity as a force that pulls masses together. That is the Newtonian picture. It works well for falling apples, planets orbiting the sun, and even spacecraft trajectories. But in modern physics, gravity is not just a force. In Einstein's general relativity, gravity is the curvature of space-time itself. Mass and energy tell space-time how to curve, and curved space-time tells matter and light how to move. That is not just a slogan. It is a very precise mathematical theory that has passed every test we have thrown at it so far, at least in the regimes where we can observe it. A black hole is what happens when space-time curvature becomes so strong that not even light can escape. The escape velocity at a certain radius exceeds the speed of light. In Newtonian gravity, you can derive a Schwarzschild radius by asking at what radius the escape speed equals the speed of light. Einstein's theory refines this idea and tells us that this radius is not just a number in a formula. It is the boundary of a region from which no information can reach the outside. We call that boundary the event horizon. The simplest black hole solution in general relativity is the Schwarzschild black hole. It is non-rotating and uncharged. It is described by a precise metric, which is a way of encoding space-time geometry. In that geometry, the event horizon is at a radius proportional to the mass, about 3 kilometers for a black hole with the mass of the Sun. If you double the mass, you double the radius. Real astrophysical black holes, however, almost always rotate. The rotating solution is called the Kerr black hole. Its space-time is more complex. It has an ergosphere, where space-time itself is dragged around by the rotation. Energy can, in principle, be extracted from that region. How do we know black holes are real and not just mathematical curiosities? We have several independent lines of evidence. One is dynamical. We see stars orbiting around invisible, massive objects. At the center of our galaxy, the Milky Way, we track the orbits of stars near a compact source called Sagittarius A Stai. Some of those stars complete orbits in just a few years. Using Newtonian and relativistic dynamics, we can infer the mass of the central object. It is about 4 million times the mass of the Sun, confined within a region smaller than our solar system. No known cluster of normal stars, neutron stars, or anything else can fit that mass into that volume without collapsing. The simplest explanation is a supermassive black hole. Another line of evidence is from accretion disks and high-energy radiation. Matter falling into a black hole forms a hot rotating disk. Friction and magnetic fields heat the gas to millions of degrees. It emits X-rays and gamma rays. We observe such emissions from X-ray binaries, where a black hole or neutron star pulls matter from a companion star. The timing and spectrum of the radiation and the motion of the inner disk match predictions for matter orbiting very close to an event horizon. We also have direct imaging. The Event Horizon Telescope used very long baseline interferometry to combine radio telescopes across the Earth. It produced images of the shadow of the black hole in the galaxy M87 and of Sagittarius A Stai at the center of our own galaxy. The bright ring and dark central region match the lensing and photon orbit predictions of general relativity. The size of the shadow is consistent with the mass inferred from dynamics. That is a strong test of the space-time geometry near the event horizon. And we have gravitational waves. When two black holes spiral together and merge, they disturb space-time. That disturbance propagates as gravitational waves. LIGO and Virgo have detected dozens of such events. The waveforms match the predictions of general relativity for merging black holes, including the inspiral, merger, and ring-down phases. The final ring-down frequency tells us the mass and spin of the remnant black hole. Again, the data agree with the Kerr solution within current uncertainties. So we have dynamical evidence, electromagnetic evidence, and gravitational wave evidence. All of them point to objects that behave exactly like the black holes predicted by general relativity. We cannot see the interior, and we cannot directly confirm the existence of the singularity that appears in the equations, but the external spacetime seems to match the theory very well. Now I want to connect this to spacetime warping more generally. A black hole is not a thing sitting in spacetime. It is a region of spacetime with a particular geometry. The warping is not just a bending in some external space. It is a change in the way distances and times are measured. Near a massive object, clocks tick more slowly relative to faraway clocks. This is gravitational time dilation. Light paths bend. This is gravitational lensing. Both effects have been measured many times, from the bending of starlight by the sun, to the lensing of distant galaxies by clusters, to the time dilation measured with atomic clocks on airplanes and satellites. In cosmology, we use the same general relativity framework, but on much larger scales. The universe on large scales appears homogeneous and isotropic. That symmetry leads to the Friedmann-Lemaitre-Robertson-Walker metric. In that metric, space-time expansion is encoded in a scale factor that changes with time. Galaxies are not flying through space like bullets. Instead, the space between them is stretching. Light traveling through this expanding space-time gets redshifted. Its wavelength is stretched along with space. That is why distant galaxies appear redder, and why we see a relation between distance and redshift. That relation, at low redshift, is Hubble's law. What drives the expansion is the energy content of the universe. In general relativity, not just mass, but all forms of energy and pressure contribute to space-time curvature. Matter with positive pressure tends to slow expansion through its gravitational attraction. But a component with negative pressure can do the opposite. It can cause the expansion to accelerate. Observations of distant Type 1a supernovae in the late 1990s showed that the expansion of the universe is not slowing down as expected. It is speeding up. Combined with measurements of the cosmic microwave background and large-scale structure, this led to the conclusion that about 68% of the energy density of the universe is in some form that behaves like a cosmological constant or something very close to it. We call this dark energy. Dark energy is not directly related to black holes, but both phenomena are about how energy and pressure shape spacetime. In the simplest model, dark energy is a constant energy density filling space. In Einstein's equations, this acts like a cosmological constant. It has negative pressure, equal in magnitude to its energy density. That combination leads to repulsive gravitational effects on large scales. It does not push things apart in a mechanical sense. Instead, it changes the evolution of the scale factor so that the expansion accelerates. We do not know what dark energy is at a fundamental level. It could be vacuum energy, a property of quantum fields in empty space. Quantum field theory predicts vacuum fluctuations and a vacuum energy density, but naive calculations give values that are many orders of magnitude larger than the observed dark energy. This mismatch is one of the biggest unsolved problems in theoretical physics. It could be that our understanding of vacuum energy is incomplete, or that some mechanism cancels most of it. Another possibility is that dark energy is a dynamic field, sometimes called quintessence, that slowly evolves over time. Observations so far are consistent with a cosmological constant, but the error bars still allow some deviation. Future surveys of supernovae, galaxy clustering, and weak lensing aim to measure the dark energy equation of state more precisely. Dark matter is another major component of the universe. It makes up about 27% of the energy density, compared to about 5% for ordinary matter. We infer its existence from its gravitational effects. Galaxy rotation curves are one key line of evidence. When we measure how fast stars and gas orbit in galaxies, the rotation speed stays roughly constant out to large radii, instead of dropping off as expected if the visible matter were the only mass. This implies a halo of unseen mass extending well beyond the visible disk. We also see evidence in galaxy clusters. The velocities of galaxies in clusters, the temperature of hot X-ray emitting gas, and gravitational lensing measurements all point to much more mass than can be accounted for by stars and gas. The cosmic microwave background provides a more global measurement. The pattern of temperature fluctuations on the sky encodes information about the composition of the early universe. The relative heights of the acoustic peaks in the power spectrum tell us how much ordinary matter, dark matter, and radiation were present. The data from WMAP and Planck strongly support a universe with cold, non-relativistic dark matter. This dark matter clusters under gravity, forming the scaffolding on which galaxies and larger structures grow. Simulations of structure formation with cold dark matter reproduce many observed features of the cosmic web: filaments, clusters, and voids. We do not know what dark matter is made of. It does not emit, absorb, or scatter light in any significant way. It interacts with ordinary matter mainly through gravity. Many candidates have been proposed, such as weakly interacting massive particles, axions, or other exotic particles. Direct detection experiments look for rare collisions between dark matter particles and nuclei in ultrasensitive detectors. Indirect searches look for products of dark matter annihilation or decay. Collider experiments look for missing energy signatures. So far, we have not detected dark matter particles directly. That does not mean they are not there. It means the parameter space is large and the interactions, if they exist, are very weak, or the masses are outside the ranges we have probed. Now I want to connect black holes, dark matter, and dark energy through the common language of spacetime curvature. General relativity says that any form of energy and momentum curves spacetime. Black holes are regions where the curvature from concentrated mass energy is so strong that an event horizon forms. Dark matter is a diffuse, invisible mass component that deepens gravitational wells on galactic and cosmological scales. Dark energy is a smoothly distributed component that modifies the large-scale curvature and drives accelerated expansion. They are different phenomena, but they all appear in the same set of equations. One question that often comes up is whether black holes could be made of dark matter, or whether dark matter could be made of black holes. The first idea, black holes made of dark matter, is straightforward. If dark matter is a particle that can cluster gravitationally, it can, in principle, fall into the same potential wells as ordinary matter. In dense regions, it could contribute to black hole formation by adding mass. But dark matter does not cool and dissipate energy the way normal gas does, so it does not collapse into disks and stars as efficiently. Most evidence suggests that the central supermassive black holes in galaxies grew mainly from baryonic processes, gas accretion, and mergers. Dark matter contributes mass, but probably not in a special way. The second idea, that dark matter is made of black holes, is more constrained. These would be primordial black holes formed in the early universe from density fluctuations, rather than from collapsing stars. If they existed in large numbers, they could account for some or all of the dark matter. However, many mass ranges are tightly constrained by observations. Microlensing surveys limit how many compact objects of certain masses can be present in galactic halos. The cosmic microwave background limits how much accretion onto such black holes could have heated the early universe. Gravitational wave detections also constrain merger rates. There is still some allowed parameter space, but current data suggests that primordial black holes cannot make up all of the dark matter over most mass ranges. This is an active research area, but it is not the leading explanation for dark matter. Another important connection between black holes and cosmology is through gravitational waves and large-scale structure. When black holes merge, they emit gravitational waves that propagate across the universe. These waves do not just carry information about the sources, they also travel through the expanding, curved spacetime shaped by dark energy and dark matter. In principle, by measuring many such events, we can use them as standard sirens to probe the expansion history of the universe. The observed amplitude and redshift of gravitational wave sources can help constrain the Hubble constant and the dark energy equation of state, independently of electromagnetic methods. We also ask how black holes themselves evolve in an expanding universe. On scales of galaxies and smaller, gravity from matter dominates over the overall expansion. Galaxies, clusters, and black holes are gravitationally bound. They do not expand with the universe. The expansion is mainly visible on scales of tens of megaparsecs and larger. Dark energy affects the rate at which structures form and grow. In a universe with accelerating expansion, structure growth slows down at late times. Gravity tries to pull matter together, but the accelerated expansion stretches space faster on large scales. Black holes inside galaxies will continue to interact, accrete, and merge, but the large-scale cosmic web will gradually freeze in. The fate of black holes over extremely long timescales involves another key idea: Hawking radiation. In classical general relativity, nothing can escape from inside the event horizon. But when we include quantum field theory in curved spacetime, something new appears. Stephen Hawking showed that black holes should emit thermal radiation with a temperature inversely proportional to their mass. This is not radiation from the interior. It is a quantum effect near the horizon. Virtual particle-antiparticle pairs that constantly appear and annihilate in vacuum can be separated by the horizon. One partner falls in and the other escapes, making it look as if the black hole is radiating. The black hole loses mass in this process. Over extremely long times, an isolated black hole will evaporate. For stellar mass and supermassive black holes, the Hawking temperature is extremely low, far below the temperature of the cosmic microwave background. They currently gain energy from the environment faster than they lose it by Hawking radiation. But in the far future, when the universe has expanded and cooled, and when most matter has been accreted or ejected, black holes will dominate the mass budget of the universe. Over timescales of around 1064 years for a solar mass black hole, and much longer for supermassive ones, they will slowly evaporate. The final stages of evaporation involve high temperatures and energetic particles. We do not fully understand the quantum gravity regime near the end, but the semi-classical picture suggests that black holes will eventually disappear, leaving behind radiation. This leads directly to the black hole information paradox. In quantum mechanics, information about the initial state of a system is preserved in the evolution of its wave function. In Hawking's original calculation, the radiation emitted by a black hole is purely thermal. It carries no information about the matter that formed the black hole. If the black hole completely evaporates and the radiation is thermal, then information appears to be lost. That conflicts with the usual rules of quantum theory. Many ideas have been proposed to resolve this paradox. Information could be encoded in subtle correlations in the Hawking radiation, or in the geometry of spacetime, or in some holographic description of the black hole. String theory and the ES-CFT correspondence suggest that information is not lost, at least in certain idealized models. But we do not yet have a fully accepted, experimentally tested resolution. This is one of the strongest hints that we need a consistent theory of quantum gravity. Now I want to connect this long-term black hole evolution to the fate of the universe under dark energy. In the standard CDM model, dark energy is a cosmological constant. The expansion of the universe accelerates but does not rip apart bound structures. Galaxies and clusters remain intact. Over trillions of years, star formation slows as gas is used up or lost. Stars burn out. White dwarfs cool. Neutron stars and black holes remain. Occasional mergers and interactions continue, but at much lower rates. Eventually, black holes dominate. Then, over incredibly long times, they evaporate. The universe becomes increasingly dilute and cold, filled with low-energy photons, neutrinos, and perhaps some stable particles, like electrons, or the lightest dark matter particles. This is often called the heat death, or big freeze scenario. It is not dramatic, but it is the natural extrapolation of current physics if dark energy is constant, and if Hawking radiation is correct. If dark energy is not constant, the fate could be different. If its density increases with time and its equation of state is less than might is 1, a scenario called phantom energy, the expansion could accelerate so strongly that even bound structures are eventually torn apart. This is the big rip idea. In that case, galaxies, stars, planets, and even atoms could be disrupted as the scale factor diverges in a finite time. Observations at present do not require such behavior. They are consistent with a cosmological constant, but our constraints are not perfect. We cannot rule out small deviations, so the big rip is a logical possibility, though not favored. Another possibility is that dark energy could change sign or decay into other forms of energy, leading to a slowing and even reversal of the expansion. That could produce a big crunch, where the universe recollapses, or a big bounce, where a new expansion phase begins. Current data, again, do not demand such behavior. The simplest fit is a flat universe with a positive cosmological constant that dominates forever. But we do not know the fundamental origin of dark energy, so we cannot be completely certain about its future behavior. Black holes in these alternative scenarios would experience different long-term fates. In a big rip, they might be disrupted before they can fully evaporate. In a big crunch, they might merge into a final, highly curved state. The details depend on the unknown physics of extremely high curvature and quantum gravity. At present, these are speculative regimes. Throughout all of this, general relativity remains our main tool for describing space-time warping. It has been tested in many ways. The precession of Mercury's orbit, the gravitational redshift of light, time dilation measured with GPS satellites, the Shapiro time delay, gravitational lensing, binary pulsar timing, and gravitational waves. No experiment has yet found a clear deviation from its predictions in the regimes we can access, but we know general relativity is incomplete. It does not include quantum mechanics in a fundamental way. It predicts singularities inside black holes and at the Big Bang, where curvature becomes infinite and the equations break down. These singularities are signals that the theory is being pushed beyond its domain of validity. We search for quantum gravity through several approaches: string theory, loop quantum gravity, causal dynamical triangulations, asymptotic safety, and others. Some of these frameworks suggest that space-time may have a discrete or emergent structure at the smallest scales. Some propose that black hole interiors and horizons have microscopic degrees of freedom that can store information. The holographic principle, inspired by black hole thermodynamics and developed in ATIS-CFT, suggests that the information content of a region of space may scale with its boundary area, not its volume. This idea has reshaped how we think about space-time and gravity. But we do not yet have direct experimental access to the Planck scale, where these effects would be most evident. We also test gravity on cosmological scales. We ask whether the accelerated expansion could be due not to dark energy, but to a modification of general relativity at large distances. Many modified gravity theories have been proposed: FFR gravity, scalar tensor theories, massive gravity, and more. They are constrained by solar system tests, binary pulsars, gravitational waves, and cosmological observations. Some are already ruled out. Others are still viable but require screening mechanisms to hide deviations from general relativity in high-density regions. Large surveys of galaxies, weak lensing, and cosmic microwave background anisotropies put tight limits on how gravity can differ from Einstein's theory on large scales. So far, general relativity plus dark matter and dark energy remains the simplest model that fits all the data. Black holes are excellent laboratories for testing gravity in the strong field regime. The orbits of stars near Sagittarius A probe the spacetime geometry close to a supermassive black hole. The Event Horizon Telescope images probe the photon ring and shadow. Gravitational wave observations probe the dynamics of merging black holes and the ring down of the final remnant. Any deviation from the Kerr solution could signal new physics, extra fields, modified gravity, or exotic compact objects. So far, the data are consistent with Kerr black holes in general relativity. But the precision is still improving. Future detectors, both on the ground and in space, will provide much more detailed measurements. There is also the question of how black holes interact with their surroundings on galactic scales. Accretion onto supermassive black holes powers active galactic nuclei and quasars. The energy released can drive jets and winds that affect star formation in the host galaxy. This feedback helps regulate galaxy growth.